People seem to have very different opinions on what algebra means. To that loudmouth uncle at Thanksgiving dinner, algebra is that stuff you learned in grade school. To your professor at École Normale Supérieure, algebra is that stuff you learned in grade school. So what the functor is an algebra? Is a ring an algebra? What if it isn't commutative? Does an algebra have to be associative? What about Lie algebras? Is a group an algebra? Then why do we also have algebraic groups? There seems to be a variety of algebras, but an algebraic variety is not an algebra. It's not even a class of algebras. Well, unless you're talking about a variety of algebras. To be concrete, an algebra is an algebra of a monad over the category of sets. But gee, I hear you say, what gives you the authority to give the definition of an algebra? Not even your algebra friends call you an algebrist. First of all, I don't know how you know that. And gee, you continue, I've read the Bible, and an algebra should really be defined as a map of infinity operads into a vibration of... You don't get it. I built this video. Down here, I make the rules. Down here, I make the threats. Down here, I'm the monad. Well, now that I brought up monads, there are probably some Redditors in the comments section writing that a monad is a monoid in the category of endofunctors. Before you post that comment, please note, every time someone makes this comment, somewhere else, this conversation happens. Besides, wouldn't it have been more meta if you had said that an algebra is a monoid in a k-linear category instead? Anyway, since I'm out here mentioning monads again, I guess I'm in obligation to make sure everyone has some idea what I'm talking about. I've already made a video on monads, but here's a TLDW over the category of sets. A monad T is a way of transforming a set X into a bigger set Tx, where you can think of the elements of Tx as being combinations of elements of X. Of course, what I just said makes no sense, and is just an intuitive handle. The actual structure and axioms of a monad express precisely what combinations are supposed to look like. It helps to have a specific example of a monad. For instance, you could take T to be the monad that associates to any set X the set of all finite-length lists of elements of X. The first condition isn't even an axiom of a monad, it's more of a precondition. The association of X to Tx must be functorial, which, among other things, says that a function f from x to y should canonically define a way of sending combinations in x to combinations in y. For example, in the list monad, we can just apply f to each element of the list one at a time. The first actual piece of structure of a monad is the unit map, which naturally identifies elements of x with trivial combinations in x. In the list monad, the unit map identifies each element of x with a singleton list in Tx. The next piece of structure of a monad is the multiplication map, which naturally collapses combos of combos into a single combo. For the list monad, the multiplication map collapses lists of lists into one big concatenated list. This structure is then subject to some rules for how the unit and multiplication interact with each other, but it suffices to say that the unit and multiplication exhibit T as a monoid in the category of endofunctors over set. Now that we've slapped together what a monad is, let's talk about the main player, the algebras. Given a monad T, a T algebra is a set A with a function alpha from TA to A called the action of the algebra. For the finite list monad, this means that an action sends a finite list of elements of A to a single other element of A. For example, we can define a list monad algebra structure on the natural numbers by associating to any finite list of natural numbers their sum. Of course, a valid action needs to respect the unit and multiplication of the monad. For example, respecting the unit means that the action should undo the unit. We can see that the natural number action does this. The sum of just one number gives that number back. Respecting the monad multiplication, on the other hand, means that collapsing combos of combos using multiplication or the action should give the same result. For the natural number action, this means that, given a list of lists of numbers, adding each sublist individually and then adding the resulting sums together should be the same as adding all the elements of all the lists simultaneously. In other words, respecting the list monad multiplication expresses that the addition of natural numbers is associative. More generally, it turns out that algebras for the list monad are precisely the monoids. So maybe you can already start to see how the monad algebras encompass actual algebras. But gee, I hear you say, you are just nitpicking and biased. Monoids just happen to be monadic over sets. Besides, monoid objects are well defined in any monoidal category, exhibited as algebras for the E1 operator. Although the list monad example exemplifies the algebraic nature of monad algebras, as does the vector space monad of my first video, you might still find it dubious that monad algebras in general describe actual theories of algebra. If you ask someone who is more normal, they'd probably tell you that an algebraic theory consists of a collection of symbols called operations, each equipped with a number called its arity, and a collection of universally quantified equations relating these operations together. Let's look at the theory of non-commutative unital rings to give this definition a little bit more context. In the algebraic theory of non-commutative unital rings, we have the following operations: a multiplication operation with arity 2, an addition operation with arity 2, a negation operation of arity 1, a unit operation of arity 0, and a zero operation of arity 0. These abstract symbols, with assigned arities, are then subject to equations expressing associativity, neutrality, distributivity, and cancellation. Now, this is just an algebraic theory. An actual algebra, or a model for the algebraic theory, is a set A equipped with a function omega for every operation symbol omega of arity n, such that every equation in the algebraic theory is satisfied universally by these functions. This means that an actual non-commutative unital ring is a set R equipped with a multiplication map, an addition map, a negation map, a unit, and a zero, satisfying associativity, neutrality, distributivity, and cancellation, as you would expect. Now, some of you, especially those who have watched one of my previous videos, might recognize this flavor of algebra as similar to that of integral domains. While there are definitely similarities, since every integral domain is also a non-commutative unital algebra, integral domains don't actually define an algebraic theory in this sense. One reason why not is because one of the axioms of an integral domain involve unequality, asserting that 1 is not equal to 0, and it turns out that this inequality is unavoidable. Algebraic theories defined here only concern themselves with universally quantified equalities. Unlike what functional programmers might tell you, monads aren't abstract nonsense for encapsulating state information. They're abstract nonsense for encoding algebraic structure. Now that I've briefly covered algebraic theories in a more historical sense, we see that this monads encode algebraic structure claim is actually two claims. First, that models for an algebraic theory define monadic category over set, and second, that the algebras for a given monad define models for a fixed algebraic theory. The first claim is easier to justify, so let's start with that. Suppose we have some algebraic theory, for example, the algebraic theory of non-commutative unital rings from earlier. Every algebraic theory defines for us a category where the objects are the actual algebras, or models of that theory, and the arrows between them are the homomorphisms. What's a homomorphism? Well, as the name suggests, it's a function of the underlying sets that preserves all of the structure. For our theory of rings, a homomorphism sends sums to sums, products to products, negatives to negatives, units to units, and zeros to zeros. Proving the first claim requires showing that any such category is equivalent to the category of algebras for some monad. The main question here is, how do we even construct this monad? Guided by the intuition that a monad associates to every set X a set of collections of elements of X, we need to use the data of an algebraic theory to take elements and build up collections of elements. A very natural guess for how to do this is to use the provided operations of the theory to put elements together. Using our theory of rings, we could associate to say the set of playing card suits, the set which contains the suits, sum of suits, products of suits, 1, 0, sums of products of suits, sums of products of suits, and so on. But gee, I hear you say, what do any of these expressions even mean? That's the neat part. They don't need to mean anything. They're what we in the business like to call formal expressions. Every distinct string of composites of operations with suits defines a unique element of this infinitely large set of formal expressions. Well, actually, this is a bit too formal. Remember that an algebraic theory also comes with equations. What we really need to do is take this gigantic mess of a set and then glue two expressions together if an equation of the algebraic theory says that they should be the same. For example, since the algebraic theory of rings insists that addition is associative, we would have to, for instance, glue these two expressions together. If you're wondering how gluing elements of a set together makes any sense at all, it helps to realize that this action of gluing is an example of a colimit. Alternatively, you can trust me. I'm a trustworthy math YouTuber, and I've never made a mistake in a video before. That would be embarrassing. Once we take all formal combinations of elements of our set and subject it to the equations of our algebraic theory, the result is called the free algebra generated by that set. The point here is that the association of every set to the free algebra generated by that set defines a monad. The monad's functoriality, unit, and multiplication are fairly natural to construct and is probably a good exercise, but it's also explained a bit more in my first monad video. What's also a good exercise is that the algebras for this free algebra monad are precisely the models for the algebraic theory. Indeed, the monad algebra action alpha serves to take a formal, meaningless expression and map it to its actual interpretation in the model. Okay, now we've gotten the easier and perhaps less surprising part over with. Given that monads are fairly abstract as mathematical concepts go, you might not find it very surprising that it is flexible enough to encompass a more historical and concrete variety of algebras. The real fun begins when we go backwards. Given some monad T, we have to try and extract from T a collection of operations, and then extract all equations of these operations that every T algebra satisfies. This doesn't exactly seem like information that just falls out of the monad multiplication and unit, because it isn't. We need some more inspiration. When lost, it helps to play around with something a lot more down to earth. Let's revisit our best friend, the theory of non-commutative unital rings. If you've taken a course on ring theory before, you might have found some parts of this definition strange. For one thing, you might have found it strange that negation is explicitly provided as an operation. Usually, a ring is only defined as having multiplication, addition, unit, and zero, and the existence of negatives is provided as an additional axiom. Maybe you were willing to forgive that one, but more prominently, you might have found it odd that I left out how addition is supposed to be commutative. The non-commutativity of a non-commutative ring only references how the multiplication does not need to be commutative, but the addition is always taken to be commutative. Despite our differences, it turns out that these two definitions are equivalent. You can use the other ring axioms to prove that negatives are automatically unique when they exist, which is probably the first exercise you were given. You can also use the remaining ring axioms to prove that addition is always commutative, even if it's not assumed. While we technically need negation to be an explicit operation for us to have a proper equational algebraic theory, commutativity of addition is something we could just give or take. This might give you the impression that the definition of a ring without the commutativity axiom for addition is better because it's more efficient. But if object-oriented programmers have taught me anything, it's that more efficient is not necessarily better. In our case, we shouldn't be afraid to introduce redundant operations and redundant equations. As long as we're comprehensive, it's good enough. For example, in the theory of non-commutative unital rings, there's no reason not to define a ternary operator called fmadd, which we think of as sending xyz to x plus y times z. We assert this interpretation in terms of other operations by adding it as an equation to our algebraic theory. More generally, Any expression on n symbols defines an operation with arity n. Another way to say this is that operations are just formal expressions in n variables. In other words, operations of arity n correspond to elements of the free algebra generated by n symbols. Since we should think of our abstract monad T as sending each set to the free T algebra generated by that set, the operations of arity n for the algebraic theory underlying our monad are just the elements of T of n. This at least covers the operations, but what about the equations? Well, the short answer is that equations in k variables correspond to commutative squares of the following form. The long answer requires a little bit of abstract nonsense. The first step is to understand that elements of T of n correspond to T algebra homomorphisms from T of 1 to T of n. This is a common generalization of many phenomena you might have encountered in algebra classes. Once you get used to this observation generalizes from individual elements to families. A family of elements of T of n indexed by a set I corresponds to a T algebra homomorphism from T of I to T of n. In fact, this property is exactly what it means for a T algebra to be freely generated. Now let's put this to use. To construct one side of an equation of operations, we are applying an n-ary operation omega to a collection of n other operations psi1 to psi-n, which we may assume have the same arity. Using our previous observations, we can now identify these selections with T algebra homomorphisms. Then, to combine these operations together, we just need to compose the corresponding homomorphisms. Now, given a square diagram like this, the two paths from T of 1 to T of k correspond to two different expressions of operations on k variables, and saying that such a diagram commutes is equivalent to saying that these two corresponding expressions are equal. Since such diagrams only rely on the language of the category of T algebras, this gives us a way of extracting the underlying algebraic theory's equations from the monad T. As a concrete example of how this works, here is a commutative square that expresses the distributivity axiom in the theory of rings. Altogether, we obtain an algebraic theory from any monad, and it's almost completely by design that the models for this theory are precisely the algebras for the monad. At last, this concludes the sketch of the equivalence between the structures of monad algebras and the structures of models of algebraic theories. If you're still here, thank you for watching. If you liked what you watched, there are formal ways to express that. If you didn't like what you watched, it must be because your algebraic structures are finitary. But you're right. I actually lied. Well, it's more of a lie of implication or something. I never finished the book on this sort of thing. But I have to come clean. When I was talking about our single-sorted algebraic theories, you may have gotten some impressions about the sizes of things. I bet you thought that all operations in an algebraic theory had to have finite arity. No? Well, I bet you thought that the collection of all operations in an algebraic theory had to form a set. Yeah, that's right. These algebraic theories presented by a monad can be infinitely complicated. For example, consider the category of sublattices and join-preserving maps. A sublattice is a set with a partial ordering, such that every subset admits a least upper bound, or a supremum. If you've never heard of these things before, that's fine. The big deal here is that the algebraic theory of sublattices has a proper class of operations. Indeed, for every cardinality kappa, the theory of sublattices has a non-trivial operation of arity kappa corresponding to the act of taking kappa many elements of the sublattice and computing its supremum. If you're part of the school of people who believe that algebraic theories should only consist of finitary operations, then I can modify my original claim just for you. Models for a finitary algebraic theory define a finitary monadic category over sets. And conversely, the algebras for a given finitary monad define models for some fixed finitary algebraic theory. To understand what a finitary monad is, let's revisit our non-commutative unital rings again. This is, of course, a finitary algebraic theory, meaning that all non-trivial operations of the theory have finite arity. But how can we see this from the corresponding free ring monad? Let's look at the free ring generated by infinitely many symbols x0, x1, x2, and so on, which in principle provides us with a set of countably infinitary operations on rings. By definition, every element of this free ring is given by a necessarily finite expression, which means in particular that each expression only uses finitely many of our infinitely many available symbols. This means that each of these elements can be thought of as coming from a free subalgebra generated by a finite subset of these symbols. Put in slightly fancier notation, the free algebra on infinitely many symbols is a union of all the free algebras on finite subsets of these symbols. Since unions are a flavor of colimit, this implies a more highbrow statement, which I won't bother to explain, but am legally required to say. The free ring monad preserves filtered colimits. This property is exactly what it means for a monad to be finitary. If we are trying to collect the operations for an algebraic theory for a finitary monad T, then we only need to take the elements of T of n for finite n. This is because, for any infinite arity kappa, the fact that T is finitary implies that T of kappa is essentially just a particular union of the Tn's for finite n. Hopefully this modification appeases the finitarians. If your stance on algebras is a bit more permissive than being finitary, but you don't vibe with a proper class of operations, the above reasoning extends to a whole spectrum of intermediate correspondences. In any case, if you still don't like the video, it's fine. If the category of fans who've got my back form a Lovert theory, then I know who the generic object is.